Okay, so now we will talk about the workout examples. And number one is let's take this out. By the principle of mathematical induction, prove that 3 power 2n plus 1 plus minus 1 power n into 2 is congruent to 0 mod 5 for all the positive integers which is our sign to denote the positive integers. And just a quick remark that for integers, A and B, A congruent to B mod 5 means 5 divides A minus B. Perfect. Let's start the solution. We know that we assume let S of n be the statement. S of n would be 3 power 2n plus 1 plus minus 1 power n to congruence 0 mod 5 where n is greater than or equal to 1. We wish to show that S of n is true for all positive integers. And for that, we must verify that S of 1 is true, is the first step of our induction. So S of 1 is true as follows, that 3 2n plus 1 plus minus 1 power and 2 is going to be 3 2 plus 1 plus minus 1 into 2, which is 27 minus 2, which is 25 congruent 0 mod 5. Perfect. This shows S of 1 is true Now we suppose that S of n is true. For some n in the dish, which is comma n is greater than or equal to 1. This means that 3 power 2n plus 1 plus minus 1 power n into 2 is congruent to 0 mod 5 for n is greater than or equal to 1. We show that S of 1 n plus 1 is true, and that is such that 3 2 n plus 1 plus 1 plus minus 1 power n plus 1 into 2 0 mod 5 is true. We show this, then we know that 3 2 n plus 1 plus 1 plus minus 1 power n plus 1 2 can be written as 3 2n plus 1 into 3 square minus 1 power n into 2, and this is 9 into 3 2n plus 1 plus minus 1 power n into 2 minus 1 power n 18 minus 1 power n into 2, and we can further write 9 3 2n plus 1 plus minus 1 power n into 2 minus 1 power n 20. Now since 3 2n plus 1 plus minus 1 power n into 2 is 0 mod 5 and 20 is also 0 mod 5, it follows that 3 2n plus 1 2 into n plus 1 plus 1 plus minus 1 power n plus 1 into 2 is also 0 mod 5. This shows that S of n plus 1 is true. Hence, by the principle of mathematical induction, the statement n of s of n is true. Now we have another exercise. Number 2. This is example 1. This is example 2, or exercise 2. So let A and B be integers such that GCD of A comma B, GCD of A comma 4 is 2, and GCD of B comma 4 is 2 also. Then prove that GCD of A plus B comma 4 is 4. Solve this. Now we know that since GCD of A comma 4 is 2, that means 2 divides A, but 4 does not divide A. That is for sure. Therefore, A is 2x for some x, some integer x, for x and z, such that GCD of 2 comma x is 1. 2 and x are relatively prime to each other. Similarly, B is 2y for y in z, and such that GCD of 2y is 1. Thus, x and y are both odd integers because they are not divisible by 2. This implies that their sum is an even integer. Sum of two odds is even, and so their sum is 2 into sum n for some integer n. Now, a plus b is 2 into x plus y, which is 4n. Hence, GCD of a plus b, comma 4 is nothing but GCD of 4n, comma 4, which is 4. Perfect. Now, we have another example. Says that let a comma b and c be integers such that GCD of a comma c and GCD of b comma c is 1. Then what we need? Then we need to prove that GCD of a, b comma c is 1. Solution. Suppose that, or if c is 0, then GCD a comma 0 is GCD of b comma 0, which is 1, implies that a is plus minus 1 and b is also plus minus 1. Thus, GCD of a, b comma c is GCD of plus minus 1 comma 0, which is 1. Now, suppose c is non-zero. By theorem 1.28 from lecture 2, maybe part 2, GCD a, b comma c exist, then let T is GCD of b comma c, a, b comma c. Also by theorem 1.2.8, there exist integers x1, y1, so we were there exist integers x comma y x1, comma y1, comma x2, comma y2, such that 1 is ax1 plus cy1, comma 1 is bx2 plus cy2. Thus, ax1, bx2 is nothing but 1 minus cy1 into 1 minus cy2, which we can write as 1 minus cy1 minus cy2 plus cy1 y2. Hence, 1 is AB x1 x2 plus C y1 plus y2 minus C y1 y2. Thus, any common divisor of AB and C is also a divisor of 1, which says that hence divisor of AB comma C, the greatest common divisor of AB comma C also divides 1. Now, since D is greater than 0, so D should be 1. So we have proven that GCD of A, B, comma C is 1. Exercise 4. We need to find the integers x and y such that 512 x plus 320 y is 64. Solution. Now we try to apply the trial and error method. So we say 512 can be written as 3201 plus 192 and 320 is 192 into 1 plus 128, and 192 is 128 into 1 plus 64, and 128 is 64 into 2 plus 0. Thus, 64 is 192 minus 128, which is 192 minus 320 minus 192, and which is 192.2 multiplied 2 plus 320 into minus 1, which is 512 minus 320.2 plus 320 into minus 1, and why we can further write it like 512.2 plus 320 dot minus 3. Hence, our x is 2 and y is minus 3. That's it. Thanks so much for attending this series of lectures. I will explain more concepts and things in this one. The next we will talk about relations. The next big thing is relations. Then we will talk about partially ordered sets. And then we will talk about functions. These could be the next 3 topics. And I will go through the lectures and then examples and the end. Thank you so much. Bye.